In this video, I will be explaining you theorem 26.3. Okay, you can see the statement: every compact subspace of a Hausdorff space is closed. Okay, first let us understand what they are saying in the statement. So here, they are talking about a Hausdorff space. Here you have a Hausdorff space, and then they are saying that inside this Hausdorff space you are having a subspace, and they are saying that subspace is what is the subspace? That subspace is compact subspace. Okay, can you understand? So there is a Hausdorff space. So for this Hausdorff space there is a subspace, and that subspace is compact. Okay, so now what you have to prove is that compact subspace is closed. That is what we have to prove. So the compact subspace present inside this Hausdorff space is closed. That is what we have to prove. Can you understand the question? Okay, so here to prove this, what you are doing is, here they are saying what is that Hausdorff space, what is that compact subspace, right? They are not talking about anything. They are just saying about it, but they are not specifying what is Hausdorff space and what is what set they are mentioning here as Hausdorff space. These things they are not saying. So in the proof you will take a Hausdorff space and you will take a subspace of that Hausdorff space you are having. Okay, everything you are going to write. Can you follow me? So here in the proof what you have to do is let because you are taking a Hausdorff space, let X be a Hausdorff space. That is the first line you will write in the proof, and in the second line what you have to do, you have to take a compact subspace, right? Compact subspace of a Hausdorff space X. That is what you have to take now, right? So that is why let capital Y be a compact subspace of capital X, this capital X. Is that clear? So what you have to prove now, this compact subspace of X is closed. That is what we have to prove, right? So here what is our compact subspace of capital X? Y, right? So that is what in the next line you will write to prove Y is closed. Is that clear? Now that is to prove Y is closed, it is enough to prove X minus Y is open. Okay, Y is closed, so when you subtract Y from this X, that will be open. So it is enough to prove Y is closed, it is enough to prove this. Okay, that is what you will write here. That is to prove this. Now you are taking a point from X minus Y, and you will take another one point from Y. You will take 2 points. That is what the next step you will write after writing this to prove. Okay, what you have to, let X naught be a point in X minus Y. This is how you have to construct a sentence. Okay, let X naught be a point in X minus Y and Y be a point in capital Y. Okay, from this you have to know something that, so here X naught is a point in X minus Y, Y be a point in Y. It means in a Hausdorff space, you know that Y is a subspace of this Hausdorff space, right? So what they are saying is, imagine this is the subspace Y. What they are saying, you are taking X naught from X minus Y. That is, when you subtract this Y, you are subtracting this space from this capital X, you will get a remaining portion, right? What is our remaining portion? This is our X minus Y. The shaded portion is our X minus Y. Am I right? Am I right? This is our X minus Y. In this X minus Y, you are choosing a point X naught. Can you understand? And you are choosing another one point, that is small y, from where? This capital Y. Okay? You are choosing a point small y from this compact subspace of capital X. Okay? That is, you are taking an element, or you are taking a point Y, small y, from this capital Y. Okay, that is what you will do in this 2 lines. Now to show what you are going to prove is, there is a neighborhood of x0. Here you have a point x0, right? For this point, there you are going to draw a neighborhood. There is a neighborhood for this point x0 that is disjoint from y. That is what we are going to prove. Okay, to prove this theorem, what you are proving? What you are proving? You are proving there is a neighborhood for what? For this point x0, and this point x0, then that is the neighborhood you are having, right? For the point x0, you are having a neighborhood. That neighborhood is disjoint from y. Okay, you know that this x0 is a point that you have in x minus y. So when you take the neighborhood of x0, that must be disjoint from y, right? Because x0 is present in this. x0 is present in the place there. You are taking x0 from here, x minus y. You are subtracting y, right? You are eliminating y portion from x. In that area only you are having x0. So when you take the neighborhood of this x0, that neighborhood will be disjoint from this capital Y. That is what you have to prove. Okay, so that is to prove the same sentence you are writing like this. That is to prove x0, our point x0 belongs to u. U means you are denoting that neighborhood of x0 with this u. Okay, x0 belongs to what? U, and u contained in where? X. This neighborhood present inside where? X minus y. Is that clear? This is what we have to prove. Okay, so if you prove this, then what condition will be proved? Y is closed will be proved. Okay, so this is what you are going to prove at the end of this proof. Okay, now to prove that, first what you are saying is you are having a Hausdorff space capital X, right? So from using that you are going to proceed further. So here what you have to do is, here you have a sentence. I did not write the sentence so that you can follow this. The reason for not writing sentences is it is my notes, right? So in my notes I don't want to write each and every lines. Okay, so that is why here I did not write each and every steps. So here you can see, after this to prove, you have to write the sentences. So what you are doing is, we are having a Hausdorff space capital X here, right? So that is why, by the definition of Hausdorff space, in Hausdorff space what you will do is, by the definition of Hausdorff space, there will be distinct points. You have to take two different points, and for that two different points you will take neighborhoods for each points. Okay, so when you take the neighborhood of these 2 points, the two neighborhoods will be disjoint. Okay, the two neighborhoods, if I choose a point here, you have, okay, if I choose a point x0 and another one point y, means I will take a neighborhood of this x0 and I will take a neighborhood for this y also. These two neighborhoods will be disjoint, they don't intersect. Okay, that is what happen inside the Hausdorff space. I am telling all these things by the definition, from the definition of Hausdorff space. Can you understand? So here, using this ideology, you are writing the next sentence. That is, what you will write is, since X is a Hausdorff space, there is a distinct points x0, y. There exist disjoint neighborhoods uy and vy respectively. Okay, this is what the sentence you have to write. And after that, after writing that sentence, you have to write the collection. Here you are having this is the neighborhood of this y, and this is the neighborhood of uy is the neighborhood of x0. Okay, is that clear? Now the collection you are having vy, right? this y belongs to capital Y is an open covering of y, because this Vy neighborhood, right, you are having Vy neighborhoods. This Vy neighborhoods are present inside the compact subspace of capital X. Okay, can you understand? This Vy neighborhoods present inside where? Our capital Y. Okay, so that is why we are writing the collection this is an open covering of Y. Okay, first you will have this Y, and within this Y you are having a point small y. You are taking a neighborhood for this small y, so that is Vy. So from this you say this Vy, okay, the collection Vy is an open covering. Open covering means for this point Y you are taking a neighborhood. Shall I explain you in the blackboard? I will explain you this in the blackboard, okay? To make you understand it clearly, I will explain it in the blackboard. So here listen. They are talking about the collection. Here you see the collection this is an open covering of Y. That is the sentence you are going to write. It means you are having a point Y. Okay, this point is present inside capital Y. You know that this capital Y is what? Compact subspace of capital X. You know that. So for this Y you are taking a neighborhood. Okay, that neighborhood is this. This is what the neighborhood. So now this is denoted as Vy. That is, this is a neighborhood of this small y, that is why it is denoted as Vy. Now you see this collection Vy is an open covering of what? It's a covering of capital Y, no? So that is what you are writing. Can you understand this? This is little bit complicated to understand it. So, but still we have to learn it, right? The examination you have to write it. Okay. Now since Y is compact, you are having Y is compact subspace of capital X. So you will come to know that this Y is compact. So since Y is compact, you know that if Y is compact, there will be finite subcollection that also covers this Y by the definition of compact. So that is what you are writing. There is a finite subcollection this that covers capital Y. Since Y is compact now, that is why it covers capital Y. Corresponding to these neighborhoods, there is some other neighborhoods also. Some other collection of neighborhood also. Look at this. Corresponding to these, there is what? Neighborhoods. What neighborhoods? There is these neighborhoods of what? Of x0. You know that. For x0, you are having neighborhood here uy, right? You are taking collection of neighborhoods of x0. So that is what here you are writing. uy1, uy2, etc. uyn are the neighborhoods of what? Small x0, such that vyi does not intersect uyi, where I varies from 1 to n. So here you know that Vyi are the collection of neighborhoods present in Y space, Y subspace. Uyi are the collection of neighborhoods present inside X minus Y space. So here you know that, so if they are like present in two different spaces means, then there is no possibility to intersect these two neighborhoods. Okay, so that is why Vyi and Uyi does not intersect each other, because this Vyi is present in their Y subspace, compact subspace. Uyi is present in their X minus Y. Okay, X minus Y. Is that clear? Okay, now let us proceed further. If we overthink it, we will get confused. Yes, it will make you confused, but still we have to learn it. Okay, let you are taking this intersection of all these neighborhood of x naught. Okay, neighborhood of x naught, you are taking intersection of collection of these neighborhoods of x naught and you are saying these equal to u. Okay, that is how you are taking. Similarly, you are taking the union of these neighborhoods of what? Small y, that is equal to what? Capital V. And is, you know that this both are disjoint and is disjoint from u. This neighborhood is disjoint from u. That is what from the above steps also you are writing. And the open set V contains y. You know that V is this. These are the neighborhoods of this y, capital Y. Okay. In the open set V, open set means neighborhood. Okay. Every open set is a neighborhood. Okay. The open set V contains y. That is within this open set neighborhood V, you are having small y. Okay. That is what you are writing. Now after that, if Z belongs to capital V, you are taking a point Z from where? Capital V. Can you understand? Okay. Implies Z belongs to V means, look at this V. Z belongs to V means Z belongs to this also. V, Y, I for some I. It means what? It is union, right? So if this Z belongs to any one of this neighborhood, okay, it can be present in any one or two or any one of the neighborhood is also okay. Right? It is not necessary to have this Z in all these VYI. Is that clear? Because this is union. That is why Z belongs to VYI for some I. I have explained you why are all okay these things to make you understand why you are putting for some I. Why you are putting for some I? Because yeah, here you have union. Union means it is not necessary to have this element Z in all the neighborhoods. Implies Z belongs to VYI means Z does not belongs to UII because they are not intersecting, they are disjoint. So if Z belongs to here means Z does not belongs to here. Implies if Z belongs to does not belongs to this means you can write Z does not belongs to U. Right? Z does not belongs to this. It means Z does not belongs to you. We can write like that, right? That is what you are writing. Therefore, here you took Z belongs to V. The same Z does not belongs to U. Therefore, you can say intersection of this U intersection V is equal to empty because there is no common elements between U and V. That is what you will come to know. So, if the intersection value of this two neighborhood is empty, you can write U is a neighborhood of X naught disjoint from V. They are disjoint. You will know that. So if it is disjoint means you can X belongs to U and U contained in where? X minus Y. So this is what we have to prove, right? So you proved it. If you prove this, then X minus Y is open. You will get. If you proved X minus Y is open, then you can say Y is closed. Okay, that is what you will write in these steps. Look at this, Y to prove Y is closed, we have to prove X minus Y is open. So that is to prove this. That is to prove this. So you proved this. Okay. I hope you understood. And also you have to try to understand by your own also. I gave you some hints. Using that hints, you also try to understand it more clearly. Try to understand the concepts. Okay. Using my points as hints, make yourself to understand more about it. Try to understand.